Okay. Hello, everyone. Myself, Puskar Pathak. I'm here to present our research work done at Skoltech with our industrial partner, Rotec. The project title is Contribution in Optimization of Abradable Honeycomb Seal Structure. In general, the welded honeycomb seals structure, they are used as a air sealing in the gas and steam turbines. They are the industrial standard clearance seal technique because of their unique design and high strength to minimum weight ratio. The thermal sprayed abradable ceramics on the structured surface have advantage of dense coating, thickness to rough inclusion, better coating adhesion, and the thermal shock resistance. Beside of these benefits, the little work has been published on the literature about the coating performance of honeycomb structure seals and their significance. So in this project, we propose to develop a thermal shock resistant structure onto the welded honeycomb seals that is produced at Rotec, as you can see in the picture, and compare their results with the conventional substrate to check the reliability of the abradable coating onto the structural surface. So based on this objective, we developed two methodology. The first one is based on the experimental. The air plasma spray technique was used to deposit the yttrium stabilized zirconia powder, also commercially known as Medco 24060NS. The spray parameters here includes the argon gas as a primary gas and the nitrogen as the secondary gas, which is sprayed using the Triplex Pro 210 plasma gun. As you can see here in the picture, the morphology of the coating of the honeycomb is structure shown in the figure A, whereas the conventional substrate shown in the figure B. A point to note is that a shadowing effect on the vertex edge of the honeycomb's structure has been observed, which plays a critical role in developing a coating layer defects near to the rib, suggesting a optimization design in the cell of the honeycomb. Also, a micro hardness test was performed to estimate the fracture toughness and check their mechanical properties. Secondly, the finite element analysis using the object-oriented technique was used to estimate the thermo-mechanical properties. As you can see on the picture on the left, the two models were developed. The size of the model were taken as similar to the one we get from the Rotec manufacturer. And the green image on the picture on the left shows the honeycomb cells, whereas the gray represents the substrate. The heat transfer analysis was done using the two boundary conditions, as can be seen on the right side. The temperature distribution, the variation in temperature from the top and bottom with the difference in the thermal flux were used as a boundary conditions. And also the model was constrained on the bottom. So based on our experimental evaluation using the Vickers micro hardness testing, the fracture toughness of the coating on the honeycomb as well as the conventional substrates were determined using the Evans and Wilson equation as shown in the equation chart in the slides. The SEM image shows the indentation mark with the crack length and the diagonal length. A larger deviation in the fracture toughness value is attributed to the irregularity of the coating microstructure, possessing a higher level of porosity within the coating. In general, it was established that the lower fracture toughness is attributed to the coating from the higher porosity association within the coating. The honeycomb seal structure, although it has a variation in the fracture toughness with the variation in the loading force, it shows the similar result with the conventional substrate. The honeycomb seal structure as a whole provide the mechanical anchoring for a coating layer when the cell act as a strain isolator. These unique features facilitate the thermal shock resistance of the applied coating. Also, the finite element simulation shows the stress drop near to the coating interface, which is due to the mismatch, the thermal properties mismatch that includes the thermal coefficient of thermal expansion. The maximum compression stress of minus 130 MPa was observed for the conventional substrate, whereas for the honeycomb substrate, it was stabilized at minus 100 MPa. The simulation results for the two Abradable seal design indicate the honeycomb-shaped structure, which is a three-dimensional structure, provides less stress level input to the substrate. Under the environment of high temperature, which improves the structure in integrity of the Abradable seal structure. On the figure on the right, it shows the variation of the thickness with the normal stress. In the finite element analysis performed showed a stress state deviation substantially at the coating substrate interface, with 25% less stress distribution within the substrate design. In conclusion, the overall project, both the experimental as well as the finite element simulation, showed a very established results. The experimental data shows the applicability of the proposed method of forming a coating layer into the three-dimensional honeycomb structure, improving the structural integrity of the Abradable coating. Also, the finite element simulation showed a potential improvement of Abradable seal design to withstand the higher thermal load conditions. Moreover, this study also reveals a need of honeycomb cell design optimization, especially at the edge vortex, where we saw the shadow effect during the spraying operation. Therefore, this can help to improve the coating integrity and the reliability of the Abradable seal structure. Thank you.